Okay, so last time we were talking about doing integrals in polar coordinates. And I'll just remind you that that wasn't our initial point of view on it. Our initial point of view was that we were going to use the polar coordinates conversion formulas as a change of variables function with which we would then do a pullback to an integral that would take place on some, pullback domain here in the r theta plane. So the change of variables approach was kind of our, initial strategy. But what we eventually saw is that once you've decided that you're going to do that, once you've decided that you're going to use polar coordinates specifically, it's just very convenient that polar coordinates is set up in a particularly nice way, geometrically simple way, and you can just see the kind of slices that you would have had to do in the r theta plane. You can just straight up see them here in the xy plane. And so just slice like so, and you don't have to pull back at all. I mean, the pullback is there. The pullback is implicit underneath the way we're going to think about it, but it's so much nicer. Instead of having to figure out what this domain looks like and then slice the pullback domain, a whole new picture that you had to draw, right? Just understand what those slices look like over here in the XY world. Right, you can see the slices right there. You can see first and last. You can see what those values of theta are, and thus your theta bounds, without drawing the pullback at all. Right, so that's just a nice kind of shortcut, you might call it, math hack for doing what is in fact still, a change of variables. Okay, so this is where we left off last time. We're going to see some more examples now. This is a nice starter example. This one comes up a lot, actually, where your domain is the entire unit disk. So how would we do this? Now, we do know that if we did this in rectangular coordinates, it would be square roots in your bounds, and nobody likes that. Okay, so let's see what it looks like if we do it, air quotes, in polar coordinates, right? So we're just we know that it's gonna turn out as an r theta integral. We know we're gonna be inserting our stretching factor of r because we are in fact doing a pullback. So you write that down, and then you realize that, what I need apparently is I need to know what's my range of values of theta. So let's just look at this picture. We're not going to draw the pullback domain. We don't need to. I can see theta slices on this picture. And I'm going to start there at 0 arbitrarily. And then my slices go like this. And they keep going all the way around until I'm done, aka until I get back to where I started. And it's tempting to call that, that first slice, if you call it 0, it's tempting to call this last slice also 0 because it's pointing in the same direction. But you do have to keep in mind that we added to theta the whole way around. And so I have to choose the last one as being 2 pi, not 0. Okay. All right, so the punchline is, though, oh gosh, I have a lot of dots to... let's do that. The punchline is that the range of values of theta, 0 to 2 pi. Is everybody on board? Okay. Good rule of thumb to remember is that if you are going to be, you might say, going all the way around, even if it's not a disk, even if it's some other shape, but if it goes all the way around the origin, right off the bat, it's 0 to 2 pi. You don't have to sort of rethink this through every such time. Okay, righty. So now, what about the r bounds? So for a given theta slice, well, the actual slice itself just looks like that. And now I've got to ask the question, what's the range of values of r? Well, r starts there, where, again, sometimes you get lucky and it's just obvious in the picture. What's the value of r at the origin? Well, that's where r equals 0. Nothing to it. The more interesting question, the last r slice of our theta slice, where's that? Well, it's on that curve, which, golly, I've got to think about the equation of that curve is. Obviously, we want it in polar coordinates because I need to know the value of the polar coordinate. And you can go to a little bit of trouble and convince yourself that the equation of this curve is r equals 1. So the last slice, that point, that curve, that equation, solve for r, and there's your upper bound. Everybody happy? Right. Okay. Alrighty, and then plug and chug, of course, and that. Now y'all know how to do the plugging and chugging, so I'm going to kind of skip over those parts. Okay. All right. So now, before we go on, I do have some tips that I think are useful that I want to advise you of before we start, doing more and more examples. Turns out, most of the time, you want to do dr d theta, not d theta dr. And it's a pretty simple reason, and that is because this variable r is usually more comfortably a function of theta than theta is a function of r. That's just how it tends to work out. There are some counterexamples, but frankly, I have to go to quite a bit of trouble just to generate a counterexample of this, and it's highly manufactured. So if you were, as I'm about to advise you, just always use the order dr d theta. I don't want to say it'll never go wrong, but I think it's a pretty safe bet that in Math212 it'll never go wrong. And I think it would be a pretty surprising case if it went wrong for you anywhere. Okay, next tip. There is a tendency for students to, step one, write down their differentials as part of sort of setting up now I've got to figure out what my bounds are, and then they're looking at pictures and they're thinking about slices and points and curves and equations, and there's a lot to do that goes into figuring out the bounds. And when you get all that done, it's tempting to kind of just proceed, and as such, to accidentally forget to insert that stretching factor. You'd be surprised how common that is. I do it myself sometimes, despite my best efforts, but more so in the past, until I thought of the following, I think, really good little mathematical life hack, which is I don't ever write down dr d theta by itself. I'll never need dr d theta by itself. The only reason I will ever write down dr d theta is as a replacement for dx dy. And dr d theta is not equal to dx dy. R dr d theta is what is equal to dx dy. That r is part of what dx dy is. That's the stretching factor that makes it all work out, right? So why would you ever write down this by itself? It's not a thing. So I advise you never, ever write down dr d theta by itself. Always write down this whole thing all at once. And if you build that habit in yourself where you know, just always write down r dr d theta, that's the thing, that's what dA is, write it down all at once, then you'll never accidentally forget the stretching factor. And I think this is pretty big, if only strategically from the point of view of, you're going to be taking a test on polar coordinate integrals, among other things, coming up pretty soon here, right? And a good way to make sure that you don't lose points, right? Because obviously this stretching factor has got to be worth a lot of points, because it's arguably the big multivariable calculus concept here in polar coordinate integrals. Everything else is kind of geometry, right? So this is a big deal, and if you accidentally forget it and it costs you, oh my gosh, it could be 4 or 5 points, right? Oh my God, it's not worth taking a chance. So that's my next little bit of advice. Here we go. Always write it down all at once. You'd be surprised how otherwise likely it is to accidentally forget it and take a nasty hit on the exam. Does that make sense to everybody? Okay. All right, and then again, how do we find bounds? Well, we identify the appropriate points, see what curve they're on, what are those equations, use those equations to solve for the bounds, just like every other kind of integral we've ever done. So here's another example. Now, I like this one a lot because of how much trouble it saves us. Let's ask, how would we compute this integral right here? Specifically computed on a domain that is this annulus, which is basically a ring. For some reason, I just like to think of this as a moat around a castle. I don't know. I've That's what I see in that picture there. Right? So how would I deal with this as the shape? Now, some students would like to suggest, okay, well, I'll compute the integral on this domain, right? And then I'll subtract the integral on this domain, right? And then yellow minus green would give us the integral on the moat. That's a reasonable, instinct, right? Something to try, and it would have worked except for one pretty nasty sticky wicket, which is that neither of these integrals here is defined. Integrals are only defined if the integrand is continuous. And very unfortunately, there is a severe discontinuity at the origin, right? It's undefined at the origin. So neither one of these integrals makes sense, and so therefore you can't rewrite the integral over the moat as the yellow integral minus the green integral, because neither one of those is a thing. Everybody see why that went wrong? This is a bummer that we can't do that, but nevertheless we really can't. If you were to say, okay, well, fine, I have to slice it up kind of the old-fashioned way, well, then you'd end up with 4 separate pieces like that. And again, nobody wants to do that. And furthermore, each one of these pieces has at least one circular edge, which means there's going to be square roots in all 4 of these integrals. This is a bad option. Okay, so look how easy it is in polar coordinate stuff. There's no problem. Very first thing we do is we write down, of course, all at once, r d theta. Don't forget that r. You'd be surprised how easy, again, and I'm going to keep trying to remind you of it as we go along, but it remains. Heads up. So r d theta, yeah, sure. Our integrand that we got from up here, see, our integrand happens to be 1 over r, and it's a weird formula in rectangular coordinates, but in polar coordinates, it's just 1 over r, so no problem. Now we talk bounds. Theta goes all the way around, so 0 to 2 pi. Any particular theta slice that we look at, that's what a theta slice looks like. Keep in mind there's a value of theta right there, and how that slices our solid is like so. And we look first at our lower r bound, which is on that curve, which has that equation, in which it's easy to solve for r. Didn't even have to do any algebra. That's nice. Oh yeah, question.
Are there any particular conditions in which it's easier to use the symmetry of theta in the bounds than it is to do all the way around? You do I guess 4 and 2.
Oh, you were thinking doing negative pi to pi or something like that?
Something like that. Yeah.
Yeah, there are some situations where that's a slick move. Absolutely. I don't want to overstate it, but I don't think that is going to come up much in our circumstances. But yeah, that can be. It can be a slick move. Absolutely. I
was wondering because the textbook a lot of they do that symmetry in all their examples. So
yeah.
Any different conditions compared to this.
Yeah.
One is purple than the other.
Yeah. There certainly are some situations. So it's hard to quantify when it's going to be useful and when it's not. But most of the time it's not. But yeah, rare circumstances for sure. Okay, let's see. So there's the lower bound. The upper bound is going to come from that point, which is on this curve, which has this equation, in which it's easy to solve for r. Upper bound 2, and we're done setting up our polar coordinate integral to represent this. And a couple of nice things happen. For one thing, there's a nice cancellation there. The r is canceled. No problem. I don't have to worry about r equals 0 because r is never 0 on this actual shape. Or said differently, you can see it right here. That cancellation's over there because r clearly never 0. It's always between 1 and 2. No problem. And then also very nice is the fact that our bounds are constants, which means this is the world's easiest integral. Gotta love it. Way better than this rectangular option, and way better than this non-existent option here that just falls flat on its face. Okay, next example. This one's a little weirder. You'll notice that we have here a disk. That green disk right there. Right, think about your algebra 2, etc. Now, very importantly, though, what we're interested in is the part of that green disk that is not in the unit disk. So you might call this green minus orange, or, take an orange bite out of that green thing. So we're just looking at the actual remainder that's left over. Altogether, then, our actual domain is this thing right here. If I can do a decent job of there. Is that cool? Everybody happy? Okay, so there's our shape, and again, rectangular coordinates would be a bummer, right? Rectangular coordinates, at a minimum, we would have 3 pieces, either like so, right? 3 separate pieces like that, or like that. So nobody wants that. Again, circular edges, square roots in your bounds, pass. So let's try it in polar coordinates. Again, RD theta. Write it down all at once. It gets your differentials on the board. It gets your stretching factor on the page. You already got credit for that stretching factor, right? Again, easy money. Don't walk away from the easy money. And let's see. Our integrand in polar coordinates. That's an easy, just conversion formula recitation there. So no big deal there. And then what's left over is to think about the bounds. So as usual, we start on the outside. Here's what a theta slice looks like. Keep in mind, theta slices are measured coming out of the origin. By the way, here's another common mistake that students will make, and that is to think of theta as emanating out of the center of whatever round thing they might be interested in, and that is absolutely not how it works, right? The theta is always measured at the origin, and so the origin's way over here, whether we like that or not, right? So our slices actually look like this. Is everybody okay with that? Is everybody happy? Yeah. Okay, so that said, let's talk about first and last slices. Well, the first one's going to be down here. Now, there is a really nice thing that happens at this point there. You could take this equation and this equation, and you could write them both down and then solve, set the one r equal to the other r and solve for theta. That works, but there's a much easier way, or at least I think an easier way, which is to observe that and that are both 1 because they're radii of that circle. And then further observe that is 1 because it's a radius of that circle. And so lo and behold, I've got an equilateral triangle right there, and I already know therefore what this angle is. That angle is pi over 3. Well, but negative because we're going backwards. We're going clockwise, not counterclockwise. So negative pi over 3 is that lower bound. Everybody see how slick that argument was? Nice move. Every so often you get lucky, so always head on a swivel, always looking out for, especially when circles are involved. Circles are awesome, right? All sorts of good things happen. So always be on the lookout for the freebies, right? That'll make your lives easier. And then likewise, let's talk upper bound this point. And again, equilateral triangle for, practically identical reasons. That means that this angle right there is positive pi over 3. Cool. Now we're going to fix a value of theta. We're going to think about the range of values of r. There's our lower bound for r, that point which is on that curve which has that equation, solve for r. Upper bound for r, that point which is on that curve, which, wait a minute, I don't have an equation for that. I have a rectangular equation for it, but I don't have a polar equation for it. So you're going to have to kind of pause and take an aside and figure out how do you convert that equation into polar coordinates. I got to do that first. And then you can come back to your process and say, well, yeah, so that point is on this curve, which has this equation, solve for r. Again, easily done because it's already done. And there's your inner bound. Yeah. How did I get the region from the definition at the top? Is it? Yeah. Okay. Yeah. Sure. So each of these is a disk, right? And if you look at what those disks are, this one is this disk right here, right? And this one is this disk right here. And what this notation here means, that backslash, that means everything that's in the left set, but which is not in the right set. So think of it as taking a blue bite out of the orange. I think it used to be orange. The blue bite out of the green disc, and that gives you this. Is that cool? Yeah. Right. All right. So plug and chug at this point, and again, just details. And yeah, there's going to be a little bit of trig in that integral. Okay, sure. But the nice thing about having trig in your integrals is that you get to use trig identities, and you get to use various little trig conveniences. There's a lot of convenient coincidences in the algebra of trigonometry. Much better than that of square roots. Okay, this next example, I'm not going to go through all of the details of it because it's not really something that's relevant to the kind of problem solving y'all are going to be having to do, so I don't want to spend a bunch of time on it. On the other hand, I really like having it in the notes because this is a calculation that's extremely cool, and it's arguably of historical significance. Because this integral is actually surprisingly important and yet surprisingly difficult. Because you can't do what they call closed form antiderivative of e to the negative x squared. You just can't write down that formula without using infinite series, power series. So, and it's not that no one's figured out how to do it. It's that it cannot be done, and this is a proved fact. Right? So, what's neat about it, this calculation, is that by taking this integral and multiplying it by itself with a different dummy variable, you can do a couple of real nice little quickies. The first little quickie I'm going to do is say this right here is it's some number. I mean, x is a variable, but this integral is a value. It's this number I'm trying to find. It's called j. It's just a number. It's constant. And constants can be moved in and out of integrals, such as this y integral. Perfectly legal. Nothing happened there. Now let's look at this expression right here, and let's ask, for the purposes of the inside integral, what can I say about this formula right here, e to the negative y squared? Well, remember, as far as the inside integral is concerned, the outside variable, in this case y, is a constant. So that means that e to the negative y squared is a constant, and constants, again, can just move in and out of integrals, no problem. It almost kind of feels like I'm breaking rules here, but I'm not. It's perfectly fine. And what we find then, the punchline is, if I'm interested in this integral right here, I can instead consider this integral right here, which I can just rewrite a little bit like so. And this integral, now by the way, I want to acknowledge, it looks like I'm making things worse. I started off with an integral that I don't know how to do. Now I have a double integral that I don't know how to do. Surely that's worse. But check this out. I can say let's do it in polar coordinates. That's how you do polar coordinates. X squared plus y squared is r squared. This domain has me going over all of R2, and this is how you would slice up R2 in polar coordinates. And you find yourself with a polar coordinate integral that's totally doable with a u substitution. Now, the guy that first thought of this a couple hundred years ago, very, very clever move. I don't think I ever would have thought of this myself, right? But anyway, it's a really slick idea, and like I say, mostly of it's slightly of historical significance because of how cool a calculation is, but also a very useful fact because when you're doing statistics, you need to know the value of this integral pretty regularly. And so knowing that it's the square root of pi, very handy fact. Okay, I guess I did it after all. Okay, questions? All right, that's cool. Okay, so we did polar coordinate integrals. Now we're going to do cylindrical coordinate integrals. And a lot of it's the same. Stretching factor, we already computed. We can do pullbacks. And now I'm just going to make that same observation that we did with polar coordinates, is that you can take, for example, theta slices. Like there's a theta slice because it's perpendicular to the theta axis. And I can see what that looks like in XYZ space. It just represents a constant value of theta, and constant values of theta look kind of like this. They're what I like to call a half planes hinged on the z-axis. That's just what theta slices look like. So again, just like with polar coordinates, I don't need to pull back and then do this kind of slicing on a brand new domain that I've got to think through and figure out what it looks like, and that can actually be quite inconvenient. Right? I don't have to. I can just do the appropriate kind of slicing in the XYZ space on the domain that I've already got and just deal with that. Okay. All right. So you do need to know what the slices look like. This, again, is what theta slices look like, and this is what R slices look like. And, of course, Z slices are just horizontal planes because, it's the same Z slices we saw with triple integrals. And so we're in business. And a couple of little quick words of advice, totally analogous to what we saw with polar coordinates. You always want your dr and d theta with dr on the inside. In my experience, there is, again, I hesitate to say never, but I have never seen a circumstance in which there was any advantage to separating the dr and d theta by like putting a dz in between them. So, for practical purposes, the only question is whether you put the dz on the outside or the dz on the inside. That's it, pretty much, right? So don't think of it as you have 6 options of how to slice. Think of it as you have 2 options of how to slice. And just pick between these 2. Next observation, again, don't forget your stretching factor. You'd be surprised how easy it is. Always include that stretching factor as part of this whole thing that you write down all at once. Because after all, that is what dx, dy, dz is. This is what a volume differential looks like if you're using cylindrical coordinates. Dr, d theta, dz by itself, not a thing. You'll never need that by itself. Why would you write it down by itself? It's just creating an opportunity to accidentally, easier than you would think, forget and thus miss a bunch of points. So it makes no sense at all, and I strongly advise that you make a deliberate habit of always writing down this whole thing together all at once, just to spare yourself your own inadvertent mistakes. And again, bounds identified by points. You can see what surfaces they're on. Write down those equations. Solve for your bounds. Example. Let's look at the upper half ball of radius A. Right, There's going to be our domain. It's this solid half ball. Again, you could do this in rectangular coordinates, but we've got our sphere there, which is going to mean square roots are going to show up in your bounds. Nobody wants that, so let's not do that. What does it look like in cylindrical coordinates here? Well, actually, it would be worse than that. Not only would you have a square root coming from this upper bound, but then furthermore, looking at your projection in the xy plane, you'd have square roots in those bounds as well. Right, so double bad. Okay, so in cylindrical coordinates, now for no particular reason, I'm going to put the drd theta on the outside and look at the dz on the inside. We'll try it the other way in just a moment, but let's do this one first. And let's see here, theta. Theta slices look like this. On this particular solid, the slice itself looks like that. Geometric appeal. Is everybody buying it? Notice we're going to go all the way around, so 0 to 2 pi. Okay, now we fix a value of theta, and we move on to thinking about our r. Range of values of r. What does an r slice look like? An r slice is a little cylindrical thing like that. But again, keep in mind, we're only interested in the r slice of our existing theta slice. So now, geometry intuition time. What does it look like when you take this cylinder and intersect it with this kind of vertically oriented quarter disc, right? And I claim the intersection is a little line segment thing about like that. So, nice fact, when you're r slicing your theta slices, the slices are really just like so. Everybody happy? Okay. All right. Starting value of r, there's the first one. It's clearly where r is equal to 0. Last value of r is going to be at this point over here, which is on this circle, which is the kind of the base of this ball of radius a, so that distance there is a. Everybody happy with that? And you get lucky sometimes and the picture just gives you the answer. Okay. And now we fix an r slice of our theta slice. So for our z bounds, all we're interested in is this r slice of our theta slice. Lowest value of z comes from that point, which is clearly in the xy plane where z is 0. The upper bound, let's see here, I'll use orange. The upper bound, that point. Thankfully, I have a picture here. That point I can see is on this sphere of radius A. In cylindrical coordinates, we've already talked about what the equation of a sphere is. You can flash back to Friday's lecture and remind yourself of that. But here's the equation of a sphere. Now again, real tricky moment. A lot of students get sort of turned around at this point. You've got to make sure to remember what it is you're doing here. Why did I write down this equation? I wrote down that equation because I'm interested in finding a z bound. And so in this equation, you need to solve for z. To get your z bound. Everybody happy? It's real easy to kind of mess that up and accidentally solve for r or something. And again, easy to mess up. So as needed, pause, remind yourself what you're doing, right? And that'll cut down on mistakes. Okay, so we did that with this order of the differentials. Now let's do the order of the differentials the other way. So now I've got my drd theta on the inside, the dz on the outside. Let's just see how this goes. And so, okay, fine. Starting with z bounds. Z slices look like that, which give me little actual slices of our domain that look about like this. So, where's the first and last of these things? And I say the first z bound is this slice, and then the last one is up there. Again, sometimes the fish jump in the boat. That's clearly where z is equal to 0. Right? We're solving for z bounds, so I need to know what z is on that slice. It's in the xy plane. Z is 0. And then the top one up here, what can I say about that point? Well, I know the value of z at that point because that is a radius, and this thing has radius a. So at that point a, at that point the height is a, I should say. Everybody good? Okay. Okay. So now we fix a value of z. We focus on this z slice. Next question, we need to look at theta. What is our theta bound? What's the range of values of theta as we do theta slices of our z slice? Here's what a theta slice looks like. I mean, of course, it's actually a plane like that, but I just need to know how that theta slice intersects my existing r slice. And so what's left over is just this little line segment. Geometric appeal. It goes all the way around. So 0 to 2 pi. Everybody happy? Okay. Great. And now on my theta slice of my z slice, I've got to ask, what's the range of values of r? Well, r starts there, which is clearly where r equals 0 because it's right there on the z-axis. And r ends at that point. What do I know about that point? Well, the picture, thank you, picture tells me that it's on this sphere, which has that equation. Now, you're going to have a temptation to think, oh, I remember what we did with that equation. In that equation, we solved for z. Well, here's the thing. Last time we saw that equation, we solved for z because we were looking for z bounds. We're not anymore, right? This is really easy to mess up, so please be careful about this. Remind yourself as needed. We are now looking for r bounds. And so in this equation, in this circumstance, we have to solve for r to get the r bound. Everybody good? Okay. All right. So, now, sadly, yeah, a square root showed up here. Brutal. And a square root showed up there. But still, I think this is better than it would have been in rectangular coordinates. There's certainly less square roots. So, I'm still going to put this in the win column. Of course, it very much depends. How good this integral ends up being very much depends on what that integrand is, which we've kind of been not paying attention to here. All right. Okay. Spherical coordinates. Same deal. Change of variables. Pull back. But you can see what the slices look like, right? This kind of slicing that I don't really want to have to do because I don't really want to have to try to figure out what my pullback domain actually looks like and furthermore actually draw it. That's inconvenient, but I can just instead see what do theta slices look like, for example. And, well, theta slices look like this. Again, it's the same as in cylindrical coordinates. It's the same theta. And then likewise, what do phi slices look like? So if I'm slicing perpendicular to the phi axis here, constant value of phi. Remember, phi is the angle off the z-axis, so a constant value of phi means we're looking at points that are a constant angle off of the z-axis, and that makes a cone. Right? either a narrow pointy cone or a wide, short cone. Well, anyway, wider or narrower, pointier or blunter, however you want to say it, depending on what that value of phi is. And that's weird. It's unfortunate. It's going to turn out not to be a problem. And then what does a constant value of rho look like? Well, rho, again, is geometrically interpreted as, distance from the origin in XYZ space. And so a constant value of rho is a piece of a sphere. Okay, so with that in mind, again, you don't have to draw the pullback. Just make sure you know what your slicing looks like in XYZ space and just go ahead and slice it up that way. So again, tips and tricks. Good news. Practically always, that's the best order to use. Let me restate that. Practically always, nothing beats this one. Sometimes there's other orders of slicing that are just as good, and that's fine, but this is the only one that I can say will almost never be beat by any other possible ordering. So I suggest you always use this ordering, and again, I got to go to a lot of trouble to find a counterexample to this, being the best choice. Yeah.
Aren't the rho slices whole spheres?
No, because so a rho slice represents a single constant value, right? So a single value of rho represents a single distance to the origin. So if I draw this, like right here, for example, if you say, well, what about all the points on the inside? What about this point here that's on this kind of smaller sphere? Well, that point corresponds to a different, smaller value of rho. Does that make sense?
I just mean, like, isn't there another complementary hemisphere on the other side of the equation?
Oh, yeah. No, that's right. Sure, this goes all the way around. Yeah. Absolutely.
So you're just
yep.
not drawing it for, like...
Yeah, that was just for sort of artistic. Yeah, right. Yeah, right. Yeah, no, I always have to kind of make artistic choices on what's going to make my picture the least muddled, in addition to various other considerations. So yeah, that was just an artistic choice. Yeah. Okay, so always use this order. Might as well. It's just your best bet, overwhelmingly. Also, very nice that if you use this ordering, the slicing works out really nicely as follows. Let's start with a theta slice. Fine, it's nice and flat, and we're accustomed to it, and that's great. Next step, we got to talk about what does a phi slice look like. Those are weird slices. I don't really like them, but in particular, what I really want to know is how do they intersect with my existing theta slice, and that's actually pretty easy. It just comes off as a little line segment. It's an angled line, but it's still a line segment, so it's flat. And it's straight, maybe if you prefer, right? And so not that bad. And then rho, of course, now at this, we've got these various different, values of rho. But if you look at, again, we have these angled but straight lines coming out of the origin that represent our phi slices of our theta slices. The rho slices just, again, represent distance moving along those lines. So it turns out that even though some of these slices are pretty scary looking, right? I don't really like these kinds of slices. What's scary about them doesn't really affect us if we choose this ordering. So again, given the shapes, that's another pretty neat argument in favor of this ordering. Again, don't forget your stretching factor. Again, the best way to not forget it is to write it down in the first place. Again, that translates to don't ever just write the differentials down by themselves. Why would you do that? It's not a thing. d rho d phi d theta doesn't have any natural interpretation for a dx, dy, dz integral. Doesn't make any sense. It's not a thing. Don't write it down. Right? So you write this down all at once. It's something meaningful, but more to the point, you therefore won't forget your stretching factor. By the way, speaking of forgetting your stretching factor, make sure you have this formula memorized, right? The polar and cylindrical formula for the stretching factor is just R. That's easy. You don't really have to memorize that. That's just a notice, But this little formula, you'd be surprised how easy it is to mess this up. I've seen rho squared sine theta. I've seen rho sine squared phi, right? And various other sort of close but no cigar versions of this. So please make sure to have this stretching factor unambiguously, crisply, clearly memorized. Okay, example. So suppose our domain is a ball. But kind of sitting on top of the XY plane at the origin, if you will. So centered up here on the Z-axis and with same radius. Okay, well, theta slices look like this. And they go all the way around, and so 0 to 2 pi for our theta slicing. Is that cool? Nice little shortcut on this. If your solid surrounds the z-axis, if the z-axis is embedded inside of your solid, then it's going to be 0 to 2 pi. Okay. All right, now the next thing that we need to do, we need to look at our theta slice. Again, here it is. Here's our theta slice, and then I need to understand what phi slices of our theta slice look like. We know that they're rays coming out of the origin, and they start like that, and then they go like this for a ways, and then things start to get weird when you get near the bottom, and it can be confusing because we're looking at a picture here where the picture itself is kind of angled from our point of view. And so, you take, this thing right here, if you look, you can see rectangular shapes on this piece of paper, but if I were to turn it and maybe, angle it some weird way, now those rectangular shapes don't look like rectangles. Right? And you can really get disoriented and have some bad geometric conclusions. So I have a little superstition on this. My little workaround of this problem is that once I have a theta slice drawn, then for my artistic convenience, I redraw that theta slice, looking at it straight on. Right? And keep in mind that this axis here, what that is that represents that way, which I'm going to loosely, sloppily, if you will, call that the R-axis. It's not really an axis, but you know what I mean. So just for sort of orientation purposes, I like to put that there. And I just find it easier to think about this picture. I find it easier to think about this picture than it is to think about that picture. And that's just a personal preference. But I think this is worthwhile. So for your consideration. With that in mind, we're going to look at this picture now. If I can get that to erase, there we go. And we're going to ask what is now, from this more convenient point of view, I'm going to ask what is the range of values of phi. And, well, our phi slices look like this. And now it's just a little easier to see that the last one is going to be there at pi over 2. And of course it was already pretty clear, but it's certainly clear in this picture as well that the first slice was at phi equals 0. Everybody okay? All right. Okay, so now as usual, we again fix a value. So we had a theta slice. Now we're going to focus on our phi slice of our theta slice. So only on this little angled line segment coming out of the origin, I now ask what's the range of values of rho. And well, again, you got to look at the different points. The starting value of rho, that point, is at the origin. Pretty immediately clear that that's 0. Ending value of rho, that point, what can I say about it? Well, it's on this curve. Wait a minute, what's that curve? That curve, don't forget, came from there. It's actually a curve that is on the surface of the sphere. Right? So it's easy to lose track of that fact, forget where your picture came from. So we're looking on the sphere itself. And on that sphere, there's some work that has to be done to get down to this. And significant amount of effort that has to go into producing this spherical equation of that sphere. Make sure that you can do that. Remember, what you're going to do is you're going to write down the rectangular equation first. The wrong color. The rectangular equation of this is x squared plus y squared plus z minus a squared equals a squared. Right? You write down the rectangular equation, and then with the rectangular equation, you can then convert to spherical coordinates per methods we talked about last week. Okay, so again, what are we doing here? I already kind of forgot, right? Well, yeah, we're trying to find row bounds. This point is the last row bound. It's on that curve, which is a sphere, which has that equation. Again, we're trying to find row bounds. So in this equation, we need to solve for row, which, lucky break, was already done. But anyway, there's our bound. What do you think? Is everybody buying it? Is everybody happy? Okay. While we're here, I'm going to make a pitch for good pictures. I think this is really important. There's just kind of no way around it. Practically speaking, now it can be done. When I was in college, I had there was this shape one time I just could not draw. And I'll leave some of the ugly details out, but I had to take a purely algebraic approach to finding bounds, and it's so hard to do it and not make mistakes. The geometry is just invisible in the algebra, and the geometry is critical in, of course, what you're actually doing. So, so hard to try to operate without a picture. So don't do that to yourselves, right? Not only should you have a picture, you should have a good picture. Little teeny tiny little postage stamp picture is going to get cluttered and confused and hard to read very quickly. Try to make it decent. It doesn't need to be publish worthy, but it needs to be at least interpretable, right? So put a little bit of effort into your picture drawing. It's really, really helpful. I like to point out that sometimes, depending on your domain, you might need to draw more than one picture, because when you make an attempt to draw your picture, there's going to be things about your first attempt picture that you don't like, because you only realized what was wrong with your picture after you drew it. Otherwise, you wouldn't have drawn it like that, right? So another way to say that is the process of drawing that first draft picture will help you understand the geometry better. Use that better understanding of the geometry that you got from your first picture to draw a better picture, right? And I do this revise and redo. Y'all can look at the notes, the pictures that I have in the notes here, and they're, pretty respectable. But what y'all can't see is the various versions of this that got erased because I realized that they were bad, right? And then replaced with better versions, which got erased, and replaced with, again, even better versions. And so these, this kind of thing that I've done here, I didn't just freehand this, just boom, just write it down, right? No, this was the result of several stages of process. Okay, so give yourself that advantage as well. And then the last thing I'm going to say is there are techniques to know. I have documented everything that I know about three-dimensional drawing in certain videos that I have on my miscellaneous topics playlist, right? I think it's good. Everything that I know, all of the ideas that are, in the background of my mind while I'm drawing, what I think are decent pictures in these notes, right? Decent. I'm not, they're not publish worthy, right? But they're decent. Everything that I'm thinking that causes me to draw precisely what I draw is in those videos. So I hope you'll give those a look. I think it's worth your time. And then don't forget, by the way, that this is not just knowledge, it's a skill. There's chops to be done. Your fingers, unfortunately, have to be part of the process, right? So practice will make your drawings just better. So give yourself that advantage as well. Okay, enough of that. So here's another example. Suppose we have another ball. This time it's centered over here on the y-axis. And that actually changes things quite a bit. So, as I see from our picture, here's what a theta slice looks like. Now, geometric appeal, I've got a ball here, and I'm taking a slice, but I'm not going through the center of the ball, right? The center of the ball is way over here. And if you take a slice of a ball that doesn't go through the center, well, you're not going to get a great circle as your slice. You're going to get a different, smaller circle as your slice. But it is still a circle. So our theta slices look like this. Now, here's another geometric appeal. And again, without the picture, I don't know how I'd make this argument. But it does not go all the way around. It only goes halfway around. And a pretty good way to persuade yourself of this is to get an orange, or I don't know if you have any. Probably don't have Play-Doh on hand in your dorms. I wouldn't think. I don't know. Not judging if you do, but some Play-Doh and a butter knife, right, would allow you can kind of chop and just kind of be like, okay, I see what that slice looks like, right? A sack of oranges is probably easier to acquire and healthier to eat, right? Anyway, I propose that what you'll find is that as this angle gets closer and closer to the x-axis, those little slices get smaller and smaller. And the very first, in fact, such slice is going to be there where theta is 0. And then theta is going to go around like that until the very last slice where theta is pi. Geometric appeal. Really helpful to have a good picture there. And again, until you are comfortable seeing that out of that picture, consider giving yourself the advantage of a three-dimensional model. Again, think creatively. How we doing? Is everybody okay? 0 to pi? Everybody's happy? Okay, so now we fix a value. Whoops, let's go back to the green. Fix a value of theta. Here's our theta slice, which again, I'm looking at a weird angle, which I don't care for, so I'm going to redraw it. Again, with the understanding that what I'm looking at there is what I'm going to loosely call the r-axis, which I draw just as kind of a reference, just kind of a visual geometric crutch, right? And now we've got to think about next question is the range of values of phi. So what do phi slices look like here? Well, phi is measured off of the z-axis, and you can see those phi slices, they start off pretty small, but then they get bigger, and then they get smaller again, the last one of which is there. So 0 to pi. Everybody see that? Yeah, cool. Okay, and now, given our phi slice of our theta slice, I now want to look at what's the range of values of rho. I'll just do it like this. Here's rho. Starting value of rho is going to be there, aka there, which is clearly the origin, where rho is, of course, clearly 0. Last value of rho is going to come from that point, which is on this curve, which of course, don't forget, is actually this curve, which means it's actually on the sphere, which means it has, well, now there's some algebra to be done here, there's some work to be done here, but that sphere has this equation. Make sure you can do that. I just yada 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 over a bunch of algebra and trig, right? And then again, solve for rho. Already solved for lucky break. And there's our upper value of rho. Is everybody happy? Okay. All right. Okay, moving along. I think this is going to be our last example here. Yeah. Oh, yeah. Go ahead.
Can you go over why phi goes from 0 to pi again instead of like 3 pi over 2 to
well, yeah, sure. So the point is, let's talk about what phi looks like itself. Phi is an angle that looks like this, right? It's an angle like that. And so when I draw like this slice right there, the actual value I'm talking about is that angle right there. And so that angle, I claim, well, the very first one is 0.
Okay.
You see what I'm saying?
I get it. Yeah. I thought I was starting with 0 as like in line with the R axis instead of in line with the Z axis. That makes sense.
I gotcha. Yeah. Okay, yeah, cool. Is everybody else? Oh, yeah, go ahead.
Why does theta in the left picture, like, why doesn't it go all the way around?
Yeah, so that's you just got to see it in the picture. But there's a couple different ways to say it. One is, remember, theta is measured off of the z-axis. There's our z-axis, and I made this observation that if the z-axis is embedded inside of your domain, then theta will go all the way around. Notice this is not. Right? So this solid that I've got here, my actual domain here, that's kind of tangent to that line, but it doesn't go all the way around it. Is that satisfying?
I think I just have to think about it a bit more.
Yeah, sadly, yeah. So, I mean, and here's a different way to think about it, I suppose, just real quick. Let's see here, pencil mode. Yeah, you got to think about, what directions can I point theta to give an actual solid slice here? And just as a silly example, what if I were to go back that way? In the negative y direction. Swing and a miss. There's nothing over there. Does that make sense?
Oh, got it.
Yeah. So, or said differently, this entire ball is in the positive y side of the xz plane. So it's all to the right of the xz plane. There's nothing to the left. Does that geometrically help? Okay, yeah, cool. Good. Alrighty. So yeah, here, last example, and again, I'm going to try not to go through all these details, but there is just a really good idea geometrically here, kind of geometric analysis, sort of intuition hack, you might say. So let's talk about what the shape of this domain is, and notice we have a couple of different requirements. On the one hand, I have here a ball. Everybody recognizes this as a ball, I hope. And in particular, that's this ball right here. So it's all of that. But what we have here, let's see, I'll do this in purple. This is not a ball. This says the collection of points that are outside, if you will, of the standard unit ball. Because this is a greater than or equal. Right? So another way to say this is that we're looking for the points that are in the orange, but that are outside of this ball. So, like this. And what points are there that are in both the orange and the purple regions? And it's I don't know what to call this. It kind of looks like a helmet of some sort, maybe. Oh, that's not a good. Let me try that again. Oh gosh. Let's see here. Something like that. Like, one of those old motorcycle helmets, like a bike helmet. It's kind of like a bike helmet, isn't it? In a way. Anyway, so there's our region, solid region, and it is hard to draw. There's a terrible flaw in this drawing that I've made here. So for one thing, this that I've drawn that looks like a kind of a vertex, it's not a vertex, right? I had a perfectly spherical melon ball. And then I took my melon baller and I took a spherical bite out of it. And that doesn't make a corner, it makes an edge. Right? So there's actually kind of a green edge going around like that. Now how do I draw that without making it look like it's kind of solid in there? It's hard to draw. Right? And then not only do I have to draw it, then I have to ask, what does it look like when I take a slice of that hard to draw thing? And it just gets geometrically very challenging, right? And easy to get confused and to mess up. So here's the way I like to think about this. I'm not going to draw the solid any better than what I've done here. But neat fact, what we have here is what I'm going to call an intersection. Our actual shape here is an intersection. I mean, different ways you can think about it. It's the intersection of the top ball with the outside of the bottom ball would be one way to think about it. But anyway, I'm just going to call that an intersection. And the neat fact is, if you need to take a cross section of an intersection, really useful geometric fact is that you can just take the intersection of the various individual cross sections. And the reason that this is a win is because these individual cross sections are actually pretty easy to draw. They're pretty easy to understand geometrically, and they're just not a challenge. And figuring out how they intersect, also not that bad. Let me just walk you through it. Let's talk about what are the various cross sections here. Not a cross section of the whole, but a cross section of the individual balls. And so, for example, this top one, what does a slice of that top ball look like? Nothing to it. Slice of that top ball is just a disc. And that's super easy to draw. Let's see here. Now, that's not the only one I care about, of course. There's also this bottom disc, ball. What do you get when I take a purple slice of this orange ball? Well, again, I get a slice. I get a half a disc, which again, easy to draw. So those are the individual cross sections. Again, notice those individual cross sections were easy to draw, nothing to it. And well, it remains that I'm trying to figure out how to take a cross section of the intersection that I don't know how to draw the intersection itself very well, and so this is equally I don't know how to do. But apparently, all I need to do is just look at how do you find the intersection of the individual cross sections, and that intersection is easy. What's in the green but not in the orange? It's this right here. Much easier to draw, right? Because the individual cross sections are easy. Does that make sense? Okay, so now as for the details, or why are these bounds equal to those, a nice little exercise. Again, think through our slicing process. Don't forget your stretching factor. So nice exercise to look at our shape and think through these bounds. Make sure you can do that If you have any questions, of course, come to office hours, right? The main reason I wanted to do this example, though, was to give you this, I consider to be very useful little drawing hack of how to figure out what that looks like. Okay. And I think that, okay, right, cool. Okay. So that's all we're going to do with coordinate system integrals. I'm going to move on now to talk about what the book calls surface area. I have a little bit of a quibble with how the book presents this. It seems to me that I don't know. This is just an opinion, right? Obviously, the authors of the book have a reasonable point of view, but I see it differently. That for one thing, they talk about two-dimensional surface integrals before they talk about one-dimensional line integrals. That seems weird to me. I'd much right? Don't you feel like you ought to start with the lower dimensional and then work your way up to the higher dimensional? Seems to me. And then they also oddly start by entertaining questions where the domain has to be one, and why. When you're trying to talk about any other kind of an integral, you don't start with assuming the integrand is one. So anyway, so I'm going to present this collection of ideas a little bit differently in a way that I think makes more sense. And here we go. So I'm going to start off with the broad question: what if your domain is a curve or a surface? Right, now let's take a quick pause. What kind of domains have we seen up to now? Single variable calculus, your domain was an interval on the x-axis. For a double integral, your domain is a region, two-dimensional region in the plane. For a triple integral, your domain is a solid in space. In all of those cases, notice that the dimensions match up. For example, an interval is itself a one-dimensional thing, and it's on a one-dimensional x-axis. An area in the plane is a two-dimensional thing, and it is in a two-dimensional xy plane. A solid is three-dimensional in a three-dimensional space. So we've been considering objects that live in kind of the space that's the same dimension that they are. And that was a luxury that we're going to now let go of. And I'm going to entertain now, for example, a one-dimensional curve that lives in a two-dimensional space. We've never seen this before as a domain for an integral. So we do not yet have a chop it up, add it up construction. We don't have a way of talking about how the whole is the sum of the parts on this kind of a domain. It's dimensionally out of place in some sense. Dimensionally inconsistent, you might say. So likewise, what if you had a curve in space? One-dimensional thing in a three-dimensional world. Weird. A surface. Two-dimensional thing in a three-dimensional world, and again, dimensionally awkward. So, and yet it remains. Sometimes I want to do an accumulation argument on one of these things. Maybe there's ants crawling all over this surface, and I want to count the ants. Right? I mean, maybe there's maybe this has a density to it, and there's more density on this surface further to the right and less density further to the left. Maybe, right? All sorts of situations where I might need to chop it up, add it up. So, okay, really all we have to do is just kind of think through. Well, what would it look like if I did chop it up, add it up on either of these surfaces? And what I'm about to write down here is not something we're going to be computing with, but this is what we're going to be representing when we start computing. This is going to be our connection to applications, is this idea of a Riemann sum. And so, for example, if I'm interested in some quantity that's, maybe I want to compute the mass of a bent wire, that where the mass per unit length is different in different places, something like that. Right. Well, I'd break it up into little pieces, a little piece like that would have a length. I could talk about, given where the location of that piece is, I could talk about the mass per unit length on that little piece. And then this product, mass per unit length times length, would tell me how much mass, or whatever my quantity of interest is, there is on that little piece. And then I would just add that up over all the pieces, and that would tell me the total mass. I chop it up, add it up. It's just like every other integral we've ever written down, except that, again, the details are a little bit different here. I mean, again, my integrand depends on location, so it's a function of two variables. But the differential, unavoidably, is just a length, because this is a one-dimensional curve, not an area. Yeah?
And this limit is as delta S is going to 0?
Yeah, that's right. And here's where I'm going to sweep some stuff under the rug. If you really want to define this carefully, then, there's some little sticky wickets in terms of how you write that down. But morally speaking, in terms of intuition, exactly what you said, just slice finer and finer, and totally. Right. Is that satisfying? Anybody else? Everybody happy? So, likewise, if you have a surface, so I've got this weird surface that's kind of bent around, it's like a piece of paper that's kind of twisted and bent in this weird way. Right? And maybe I want to measure how much mass is on that thing, or what have you. Well, I'm going to break it up into little pieces. Each little piece has an area. It doesn't have a volume. Right? We're in 3 dimensions, but it's a surface. It doesn't have volume. It has area. And then on that surface, I can talk about, mass per unit area, or ants per unit area, or whatever quantity in question per unit area. Right? So the actual pieces, what am I actually talking about on each little piece here, is going to be given by this expression. But note again the dimensional inconsistency. This is a function of 3 variables because it depends on location, which is 3-dimensional. But the appropriate notion of size is 2-dimensional. So, anyway. And then just a little bit of notation. I think this, pretty believably, would be rewritten as that. It's just notation, just a shorthand for that Riemann sum. I think this is a pretty reasonable shorthand notation for that Riemann sum. And now the only question that remains is how do we actually compute these things? And that'll be a topic for tomorrow. So, we'll draw the line right there. And, see you tomorrow. Have a good one.